everybody. That vector equation describes simple circular motion, and the purpose of this investigation is to figure out why. It shouldn't come as a surprise because we've actually done this once before when we were studying parametric equations. In that context, we already knew that your x of t equation is cosine and your y of t equation is sine if you want to produce a circular motion. And all we've done is rewritten those two equations as a vector. It's like, what should the horizontal component of our vector be? It should be the equation that tells us x. And the vertical component of our vector should be the equation that tells us y. So that's all we've done up here. But let's go through the process and rediscover it in a different way. So I could plug in a couple of different times here and notice that time is occupying the place that I would usually put an angle in cosine and sine. And also remember that cosine is the function that converts an angle into an x-coordinate of a point on a unit circle. So in other words, what I mean is, if I have an angle here, cosine of that angle tells me the x-coordinate of that point. And sine converts an angle into a y-coordinate of a point on a unit circle. So let's fill in this column of the table. So all I've done is I've just plugged in the times into the horizontal and vertical components. Let's actually evaluate them though. So angle 0 corresponds to this direction, so cosine would give us 1 and sine would give us 0. So that's the vector 1, 0. And I could sketch that this way. So at time 0, I have that vector. Let's actually sketch it here. So then at time pi over 4, that corresponds to 45 degrees. So that should be root 2 over 2, root 2 over 2. And so that would look like this vector that points at 45 degrees and has length 1. When the angle's pi over 2, that points straight up and would give us the vector 0, 1. At 3 pi over 4, it points 45 degrees in that direction, and so I would have negative root 2 over 2, root 2 over 2. And then the angle of pi is the same as 180, so it points straight to the left. So if you can sort of imagine a flip book going from this vector to this vector to this vector to this vector to this vector, it is as if this vector is slowly rotating around a half circle. Let's fill in each of these little mini vectors here. So that vector would go here, then we've got the one that's straight up, then we've got the one that's that direction, then we've got the one that's straight left. I wouldn't want to just connect these with straight lines, because remember, we're only sampling, or we're only seeing what these vectors are at some selected times. If I wanted to, I could plug in a time that was halfway between these, so pi over 8. And that would give me a vector that was an angle that was halfway between them. So if I was going to fill in the intermediate times, it would actually end up making a complete half circle. And remember, what we're always doing with these equations is we're imagining as time ranges over all the possible times, we'll have a bunch of vectors, but we're treating them as position vectors, which means that we're starting them at the origin, and then we're looking to see where does the tip of the vector point to. And we're going to connect all of the different places that the vectors point to, and that's going to be our path. So this is creating a circuit. So from time 0 to pi, it's creating a circular path that goes in this direction. If we were going to extend time past pi, it would create the rest of that circle.